Green hydrogen has long been seen as the cornerstone of a clean energy future, a fuel capable of powering heavy industry, transportation, and even aviation without carbon emissions. Yet one stubborn barrier has kept it from going mainstream: cost. Producing hydrogen from renewable electricity still costs between $4 and $6 per kilogram, far higher than the $1 to $3 range for hydrogen made from natural gas. The global industry has therefore focused on an ambitious target, $2 per kilogram, as the tipping point where green hydrogen becomes commercially competitive. Reaching that milestone requires progress on every front: cheaper renewable electricity, more efficient electrolysers, longer lifetimes, and lower material costs. While most headlines focus on renewable power or electrolyzer scale, the biggest bottleneck has quietly been sitting inside the stack, in the form of one of the rarest elements on Earth: iridium. Iridium is a precious metal used as a catalyst in proton-exchange-membrane electrolysers, also known as PM electrolysers. These systems are vital because they can respond quickly to fluctuating renewable electricity and operate at high pressure, but they depend on thin layers of iridium to split water efficiently. Global iridium production is tiny, only about 7 or 8 tons per year, and demand from hydrogen manufacturing is expected to skyrocket. That scarcity drives up costs and threatens to limit how quickly we can scale green hydrogen. This is why a recent breakthrough from the Netherlands has drawn so much attention. A materials science company called VSParticle, working in partnership with Plug Power and the Center for Clean Hydrogen at the University of Delaware, has developed a new catalyst layer technology that slashes iridium use by up to 90%, without sacrificing performance or durability. The results were verified through independent testing, showing impressive stability and high current densities suitable for commercial use. At first glance, cutting iridium loading by 90% might sound like a small materials improvement. But in the economics of green hydrogen, it's massive. Every gram of iridium saved translates directly into lower electrolyzer cost. For a technology that could soon deploy at gigawatt scale, those savings multiply into billions of dollars. And when you combine cheaper electrolysers with cheaper renewable power, you move much closer to the $2 per kilogram goal that defines the future of clean hydrogen. Let's unpack how this works. In a conventional PEM electrolyser, iridium is used in the catalyst layer that drives the oxygen evolution reaction. Historically, these layers have used around 1 milligram of iridium per square centimeter of electrode area. VSParticle's breakthrough brings that figure down to around 0.1 milligrams, a tenfold reduction. At the same time, tests show that these nanoporous layers maintain high performance. Operating voltages around 1.74 volts at 3 amps per square centimeter, and degradation rates of less than 2.3 microvolts per hour across thousands of hours of operation. In simpler terms, the system performs as well as, or better than, traditional designs that use 10 times more iridium. That is the real milestone. Because the performance gap between research and commercialization is often wide, but here the breakthrough is already meeting industrial metrics verified by a major manufacturer, Plug Power. Why does this matter for cost? Hydrogen production costs are driven by 3 primary levers: the cost of electricity, the capital cost of electrolysers, and their operational lifetime. Reducing iridium use directly impacts capital cost. Iridium alone can represent a significant share of stack material costs. If you can maintain the same output using 1/10 as much, you cut costs dramatically. On the manufacturing side, cheaper catalyst layers mean lower overall cost per kilowatt of electrolyser capacity. This improves project economics, raises return on investment, and accelerates deployment. But perhaps even more importantly, it makes the hydrogen sector scalable. You can build 10 times as many electrolysers using the same global iridium supply, which means faster adoption, more competition, and steeper cost declines. Let's put numbers to it. A 100 megawatt electrolyser plant built with today's technology might cost roughly $800 per kilowatt in capital expenditure. If improved catalysts like VSParticle's reduce stack cost by 20 to 30%, that brings total capex closer to $600 per kilowatt. Combine that with improving efficiency, from 55 kilowatt hours per kilogram of hydrogen to 50, and longer lifetimes that have stack replacement frequency, and the levelized cost of hydrogen begins to fall sharply. Under favorable conditions, such as renewable power priced around $30 per megawatt hour, this combination of improvements can drive hydrogen costs down from around $4 per kilogram to just above $2.50 per kilogram. With additional efficiency gains and larger plant scale, the holy grail of $2 per kilogram becomes achievable, especially in regions with abundant solar or wind energy. Beyond the numbers, this breakthrough also addresses a major risk factor for investors and policymakers: supply chain fragility. Iridium scarcity has long been viewed as a hard limit on the scalability of PEM electrolysers. If you need several tons of iridium per gigawatt, and global supply is less than 10 tons, large-scale deployment becomes impossible. Reducing iridium usage by 90% changes that calculus entirely. Suddenly, multi-gigawatt deployment becomes feasible without exhausting global resources. That improvement reassures financiers, reduces perceived risk, and helps secure capital for hydrogen projects. Durability is another critical advantage. Electrolyser stacks degrade over time, which drives up maintenance costs and downtime. In testing, VSParticle's nanoporous electrodes maintained performance over thousands of hours with minimal voltage increase, a sign of excellent durability. That longevity translates directly into fewer replacements, lower operating costs, and higher uptime, all of which improve the levelized cost of hydrogen. From the perspective of developers and consultants using tools like H2Hub, ReneEnergy.com, this kind of innovation is exactly the sort of variable that belongs in a modern cost modeling framework. On H2Hub, professionals can simulate how changes in catalyst loading, capex, efficiency, and lifetime influence the cost per kilogram of hydrogen. A single line in the spreadsheet, iridium loading milligrams per square centimeter, becomes a major driver in whether a project achieves $3, $2.50, or finally $2 per kilogram. Imagine modeling a 500 megawatt hydrogen plant. With legacy technology, your financial model shows $4 per kilogram at an electricity cost of $40 per megawatt hour. Adjust the catalyst input to reflect VSParticle's innovation, and suddenly the same plant might yield hydrogen for $2.4 per kilogram. Add cheaper solar power, and you could hit the $2 per kilogram threshold years ahead of schedule. For engineers, this is more than a materials breakthrough. It's a design paradigm shift. With lower precious metal content, stack manufacturing can scale faster, logistics become easier, and supply chain bottlenecks shrink. For policymakers, it supports localization strategies, because the dependence on rare imported metals diminishes. For investors, it makes hydrogen projects less risky and more bankable, since they are no longer tied to volatile iridium prices. This also accelerates what economists call the learning curve effect. As manufacturers produce more electrolysers, costs fall through economies of scale and process learning. If iridium supply no longer caps production, companies can scale freely and learning rates accelerate. That's the same dynamic that drove solar modules from $4 per watt to under 30 cents per watt in just over a decade. Hydrogen is now entering that same transformation stage, and materials science is lighting the fuse. At the system level, these savings ripple outward. Lower stack cost reduces the total project capex. Lower risk improves financing terms. Lower O&M costs improve margins. Collectively, those improvements bring hydrogen's levelized cost ever closer to $2 per kilogram, which is the global benchmark for competitiveness. The collaboration between VSParticle and Plug Power is also a model for how innovation ecosystems should function. Small research-driven firms providing advanced materials, paired with major industrial players capable of scaling production and commercialization. With pilot integration planned in the next development cycles, this isn't a distant vision for 2040. It's a near-term shift that could start influencing real projects by 2026 or 2027. For your professional community at H2Hub, ReneEnergy.com, this milestone offers an opportunity to teach how deep tech breakthroughs translate into financial impact. Courses and templates can now incorporate materials risk reduction as a measurable input. Students and professionals can explore how reducing rare metal dependency affects financing, supply chain confidence, and geopolitical stability in green hydrogen markets. On the policy side, this development could also reshape subsidy strategies. Many governments offer incentives based on hydrogen output or carbon reduction, but rarely on material innovation. As breakthroughs like this demonstrate their economic importance, we may see policy frameworks rewarding resource efficiency, not just carbon efficiency. In the broader picture, this is a reminder that the clean energy revolution is built as much in materials labs as in solar fields. The transition to renewable fuels depends not only on generating electricity cheaply, but on converting that electricity efficiently and sustainably into hydrogen. Every improvement at the atomic level, every reduction in iridium, every increase in catalyst surface area, every gain in durability, compounds to lower the global cost curve. It's easy to forget that the solar industry once faced similar challenges. In the 1990s, silicon wafer production was costly and limited by purity constraints. Then came breakthroughs in thin film deposition and nanostructuring, which reduced materials use while improving performance. The parallels are striking. Hydrogen technology is now undergoing its own thin film revolution. By controlling catalysts at the nanoscale, we can produce the same performance with far less material. And while many headlines mention the potential for $1 hydrogen, a figure likely achievable only under exceptional conditions. The path to $2 per kilogram hydrogen is real, measurable, and now within reach. That price point could transform the global energy system. At $2, hydrogen can replace fossil fuels in refineries, power plants, and chemical industries. It becomes economically feasible to produce green ammonia, e-methanol, and sustainable aviation fuels at scale. It also enables countries to trade hydrogen and its derivatives across borders competitively, creating a true global clean energy market. In this sense, the VSParticle and Plug Power partnership isn't just a laboratory success, it's an inflection point. It shows how collaboration between nanotechnology and industrial engineering can directly influence macroeconomics. It demonstrates that solving a materials bottleneck can accelerate an entire industry. For the hydrogen community, this is a signal that the next phase of competition will be driven not just by scale, but by chemistry, by who can make the most hydrogen with the least material. It's a race toward efficiency at the molecular level. At h2hub.reneenergy.com, this story can serve as a flagship example of how innovation and economics intersect. The platform can showcase how a single research breakthrough feeds into real-world project models and financial outcomes. It's an opportunity to educate developers, investors, and policymakers about why materials science belongs at the heart of hydrogen strategy. Looking ahead, if this innovation scales globally, we could see a cascade of effects: increased electrolyser production capacity, reduced dependence on scarce metals, and more affordable hydrogen worldwide. Within a decade, hydrogen could achieve what solar achieved in the last one: rapid cost collapse through innovation, replication, and scale. Ultimately, a 90% reduction in iridium usage might sound like a technical detail, but it's a symbol of what's possible when science meets necessity. It proves that the biggest leaps forward often come from the smallest layers of material, nanometers thick but economically transformative. The path to affordable hydrogen won't be built by one technology alone, but by a convergence of breakthroughs like this one. Smarter membranes, better catalysts, cheaper heat integration systems, and advanced digital optimization. Together, they form the mosaic of a cleaner future. As we edge closer to that future, the story of VSParticle and Plug Power reminds us that green hydrogen's destiny lies not just in megawatts, but in materials. Not just in ambition, but in atomic precision. And when those align, the dream of producing clean fuel for $2 per kilogram becomes more than a goal. It becomes a reality within reach. For engineers, developers, and investors who want to model this impact in their own projects, visit h2hub.reneenergy.com, the platform that turns innovation into insight and insight into implementation. There you can explore cost templates, financial models, and scenario tools built to capture the real-world impact of breakthroughs like this. Because the future of hydrogen isn't defined only by the price of electricity. It's defined by the ingenuity of the materials that make clean energy possible. And if this iridium reduction breakthrough delivers on its promise, it won't just lower costs, it could redefine how the world thinks about the economics of green energy forever.